This video is on path analysis with a primary focus on mediation and moderation effects. When you have a theoretical model with observed variables, there's basically two different approaches you can take. The first one is use traditional regression methods. Basically here, you basically solve each equation one at a time using ordinary least squares. The limitation here is to estimate all parameters in the model. Unlike path analysis, where you can actually fix things at zero, just for full and partial mediation effects, for example, you have to estimate all paths. Your next step is basically have no model of overall fit. And basically the reason for that is you've estimated every parameter possible, so your model is saturated. Your only true measure of model fit is your R-squared statistic. For path analysis, it's a little bit of a different approach. Here, you estimate every parameter in the model simultaneously, whether it's using ML, MLR, or a wide range of other estimators. Moreover, you have multiple dependent variables, mediators, moderators. Again, these are all going to be all estimated within a single model rather than running a series of regression models to test the same question. The other benefit to path analysis, you can actually fix values at zero or some other value. For example, again, you can assume a full mediation and fix the relationship between x and y at zero. Another benefit is you can actually determine the overall model fit using your chi-square, CFI, TLI, RMSEA. But again, remember your R-squared statistic, which is how much variance in that endogenous variable can be explained by the exogenous variables, is also a measure of model fit. The last great thing about using path analysis is you can easily incorporate what are called auxiliary variables to predict missingness. Again, remember, whenever you're using path analysis, SEM, whatever with an M+, your data are going to be all estimated using some form of FIML. Again, it's full information, maximum likelihood. It's important to remember that path analysis and regression are very similar types of models, as you'll see later. As you might expect, the model assumptions are the same for path analysis and for multiple regression. First off, the first assumption is your variables are measured without any error. Again, your variables should be error-free. If your variables actually did have error, then you would estimate that model using SEM, because you have latent variables. Your next assumption is you assume your model is correctly specified. Now, the order of those variables is correct and theoretically defensible. Next, you assume you have no multicollinearity problems. Just like in multiple regression, multicollinearity has the same effect within path analysis. Basically, it's hard to interpret the effect of one variable on the other when those two variables are so highly correlated. As a result, it may appear as though neither variable predict the endogenous variable very well, when in fact they both do when looking at bivariate relationships. You also assume multivariate normality, but again, that assumption can be relaxed when using robust estimation methods like MLR. You also assume your variables are linear related, but you can relax that assumption by testing nonlinear models. For example, you could add quadratics, which is basically taking your x variable and squaring it and including the x variable and x squared in that path model. Next, you also assume your variables are additive, basically meaning there's no interaction effects. However, you can relax that constraint by adding interaction terms to your model. In the end, what it comes down to is you're making the assumption the model is actually correctly specified. The primary purpose of path analysis is to test a theoretical model and how these observed variables are related to one another within a single model, rather than doing a bunch of separate models like you would have to do within multiple regression. when testing path analysis models, you basically follow 3 steps. The first you want to do is test whether your current model was specified correctly. You basically do this by looking at your overall model fit. So your CFI, TLI, RMSEA, and so forth. It's important to remember that your overall model fit is only a prerequisite to look at your relationship between variables and your overall contribution. In other words, steps 2 and 3. Given that having a good overall model fit does not imply a good model, in step 2, you really want to look at how those observed variables are related to one another. Both you look at the unique contribution and the partial contribution. Think of a unique contribution as more of a simple regression model, where you have one x and one y. Just how well does that one x predict that y variable? Your partial is more of a multiple regression problem. So you want to know what's the effect of x1 on y after controlling for x2. In step 3, you not only care about unique and partial contributions, but you want to know how well do all the variables in the model, how do all your x variables predict your y variables. In other words, you're looking at your overall r squared, or how much the variance in that y variable can be explained by the associated predictor variables. The first step in path analysis is model specification, and basically it's drawing a diagram or writing out the equations of how your variables are all related to one another. At this point, you determine what your exogenous, endogenous, mediators, moderator variables are, and so forth. And more importantly, how those variables are related to one another. For example, does x1 predict x2, which predicts y? Or does y predict x1, which predicts x2? Or do x1 and x2 both predict y? Although it's often called causal modeling, remember, it's only causal in theory. You can only really test whether it's actually causal using experimentation. After you determine how you want to, or what model you want to estimate, your next step would be to choose the estimation method and test how well that model actually fits the data. More often than not, you have to make model changes based on modification indices, as it's often hard to perfectly estimate or determine how a model should be specified. For example, do you estimate a full or partial mediation model? Many people will actually test for the full mediation. If you have a poor model fit, only then will they constrain the relationship between the x and y variable to test for a partial mediation. With that said, it's important to remember that just because you have a good model fit doesn't mean you have a good model. All it basically means is your model is able to reproduce the sample covariance matrix. In other words, there's no difference between your sample and predicted covariance matrices. It's also very important to remember that you could always have alternative models, and that one model is always going to be wrong to some degree. In other words, it's wrong because you're either missing variables or they're predicted in the wrong order. Depending upon your model fit, you may need to do either model trimming or model building. In other words, trimming, what you might do, is if a path coefficient was near 0, you might actually fix it at 0 to create a more simple model. Conversely, you might need to do model building. In other words, if you have a poor model fit, it might imply that certain paths you fixed at 0 aren't in fact 0 and should be estimated. Your Lagrange multiplier test is based on your modification indices within M+. what that tells you is should you be adding certain paths to the model. Your while test is testing whether if you were to drop a path, in other words, fix it at 0, what would be the change in your chi-square? Again, you can easily do that by comparing a model with the constraint and without the constraint. Regardless of whether you add or remove paths from the model, it's important to always justify it based on empirical and theoretical specification. In other words, empirically, is it supported by the data? In other words, should you really fix a path at 0 or estimate it? In other words, in fact, is that path non-zero? Whereas theoretical would be based on theory, should those paths be estimated or fixed at 0? More often than not, you hope your theory matches your statistics. Regardless, whenever possible, it's always important to do cross-validation. So in other words, develop the model based on one sample of data and then test it on another. As you've seen in the past, MPlus and other SEM software packages will give you both standardized and unstandardized coefficients. And the question is, which one do you report and which one do you focus more of your attention on? Remember, your standardized coefficient puts all your path coefficients on a comparable scale. In other words, all your variables are standardized and have a mean of 0 and a variance of 1. As a result, it's really easy to determine which variables contribute more than other variables because your slopes, or regression coefficients, are comparable across models. However, it's often very useful to look at your unstandardized coefficients. In this case, you actually care about the original units of the data and actually want to predict the dependent variable or endogenous variable. For example, if you wanted to use employee salary and satisfaction to predict work productivity, you actually want to use the raw data to get a predicted Y value. It wouldn't be very useful to get a predicted standardized Y value. Unstandardized coefficients are also very useful for invariance testing, or testing whether the relationship between variables differs across groups. Within path analysis, you tend to see people only use betas, gammas, and phi coefficients. Your betas is your relationship between your endogenous variables. Your gamma is how your exogenous and endogenous variables are related. And phi is based on the relationship between your exogenous variables. To make things easier, we also often give numbers to those coefficients. For example, gamma 3,1 is a relationship between. It's important to remember that a path coefficient is interpreted the exact same way as a regression coefficient. If you have a partial regression coefficient, you're basically testing what's the effect of x1 on y controlling for x2. Or if you had a simple regression, we only have x1 and y, just what's the effect of x1 on y. You could also have non-directional paths with a double arrow, which is basically the same thing as a correlation, again standardized, or covariance, unstandardized. At first glance, this model might look rather complex, but when you break it down, it's quite manageable. For example, phi1, 2 is simply a correlation between x1 and x2. Next part of the model is you have x1 and x2 predicting y1. Well, those are gamma coefficients, so gamma 1, 1 is the effect of x1 on y1 controlling for x2. Beta 1, 2 is a relationship between y1 and y2. Again, that's a simple regression. Next, we have the effect on y3. Again, it's a simple correlation because only one arrow goes into it. So beta 2, 3 is interpreted the exact same way you'd interpret a simple regression model. Y4 has two arrows going into it, one from y2 and one from y3. As a result, beta 4, 2 is interpreted as what's the effect of y2 on y4 after controlling for y3. Now that you have a fairly good idea of what path analysis is, our next step is to introduce mediation effects. A mediator variable, also called intervening or process variable, really makes the assumption that the relationship between x and y are not directly related, but instead only occur through the mediator. In other words, the relationship between x and y would not occur if it wasn't for the mediator variable. Perhaps the most simple example of this would be pain. If someone were to pinch you in the arm, which is going to be your x variable, your response would be to say, ouch. So, however, this would not occur if chemicals weren't released in your skin, which send a signal to your brain, indicating a response of pain. So again, in this case, feeling pain, having those pain receptors, is really your mediating variable, because you wouldn't say ouch if you didn't have the pain receptors. Here's a simple example I found in the literature, where they theorized that technology predicts knowledge management, which predicts organizational effectiveness. What they're basically arguing is that the relationship between technology and organization effectiveness wouldn't occur without knowledge management. There's basically two different types of mediators, a full and a partial mediator. A full mediator implies the relationship between x and y disappears after controlling for your mediator. A partial mediator means that x and y are still related even after adjusting for that mediator variable. However, the relationship between x and y does decrease as a result of incorporating that mediator in the model. It's a little easier to understand partial versus full mediators based on a diagram. Here, our x, or independent variable, is no longer related to our y, our dependent variable, after incorporating the mediator. So basically, the IV predicts the mediator predicts the dV. The relationship between the IV and dV is no longer existent, it's basically zero. It's called a full mediator. A partial mediator implies that even after adjusting for the mediator, there is still a relationship between your independent and your dependent variable. Again, gamma 2, 1 should be smaller, but nevertheless, that path is still significant. When testing this simple mediation model, you could really follow a three-step process. Your first step is you want to know what's the bivariate relationship between x on y. In other words, that gamma 2. In theory, x and y should be highly correlated. Your next step will be to regress x on m. That's also a simple regression, where gamma 1 is the effect of x on m. Step 3 is you're testing a multiple regression model now, where you have what's the effect of x and m on y. Here you have beta which is the effect of m on y controlling for x, and you have gamma 2 prime, which is basically the effect of x on y controlling for m. Based on Baron and Kenny's approach, you really want to know, is beta 2 prime different from beta 2? Perhaps more importantly, though, is you really want to know, is beta 2 prime now 0? Thus implying the relationship between x and y can go fully through the mediator. However, if beta 2 prime is significant, you would then have a partial mediator. There are a few important terms to remember when looking at mediation effects. The first one is your total effect, which is the sum of your direct effect, which is gamma 2 prime, which is between x and y, after adjusting for m, and your indirect effect, which is basically the mediation effect, or the product of gamma 1 and beta. When testing for a mediation effect, several things have to hold. The first is that x has to be related to m. That gamma 1 has to be significant, and for most practical purposes it should be large, typically greater than 0.3. Next, m has to predict y when including x in the model. In other words, that's your beta. So the effect of m on y should be significant and large when controlling for x. If you're using a regression model, that should result in a large change between gamma 2 and gamma 2 prime. However, if you're doing path analysis, that can easily be fixed at 0, and then your chi-square, so your change in chi-square, is an indication of whether that change is actually 0. Historically, although more recently it's argued against, is that x really should be highly correlated with y. In other words, x should predict y as well. There's a tremendous amount of information out there on mediation effects. A great simple example is the Baron and Kenny webpage. However, the James article is also really great in terms of understanding how mediation differs when looking at it from a regression approach versus a path analysis or SEM approach. It basically describes the benefits of being able to test multiple mediators simultaneously, as well as having multiple outcome variables, in terms of really understanding the complex relationship between those variables. Moreover, it's much quicker and easier to do within a path analysis or SEM model than within a series of regression models. One attractive feature of using path analysis, or SEM for that matter, is that all the effects, your direct effect, indirect, and total effect, are provided for you. If you need a bunch of regression models, not only is that more time consuming, but you actually have to compute all your direct, indirect, and total effects by hand. Another great benefit to using software like M+ is that it's really easy to compute the standard errors using different methods. For example, it's relatively controversial in terms of the best way to estimate your standard errors. Remember, your standard errors are used to compute your test statistics. You divide your parameter estimate, your path coefficient, by your standard error to get your t or z value. In most cases, most research suggests that the bootstrap standard errors tend to work the best, and I'll show you those in the M+ code later. However, you could also use MLR, which is often a good alternative. If you want to understand your indirect effects, in other words, your mediation effects, those two terms mean the exact same thing, you can do it using a number of different different commands within M+. Under your model indirect command, you can either use IND for indirect or VIA for via certain paths. Regardless of which approach you take, or whether you even test for the indirect or mediation effects, those will not influence your model fit statistics or any of your parameter estimates. These are only additional results provided by M+. Here's a relatively simple model where you have one exogenous variable and 4 endogenous. Of those 4 endogenous, 3 are really thought to be mediating variables. The indirect statement, which is what I often commonly use, is to basically test specific indirect effects or mediation effects. Here, the variable on the left-hand side of the indirect effect is your dependent variable. The one on the far right-hand side is your independent variable, and the one in the middle will always be your mediator variables. Our example before is you can see that y is on the left-hand side, x is on the far right-hand side, and the mediator is in between. So it's really testing the relationship between x and y. When using the IND statement, there's basically 2 different approaches you can take here. The first one in blue, which is y2 IND x1 under the indirect statements command, basically tests all the mediation effects between x1 and y2. Those are indicated in blue. The other approach would just be only testing those indirect effects that you're most interested in. For example, here in orange, you're looking at whether y1 mediates relationship between m2 and y2. Again, the first one, y2 indirect x1, is basically a more efficient way of testing a bunch of mediation effects all at one time, where the one in orange is testing only those of primary interest. As you can see here, the one in blue has many mediation effects, 5 to be precise. And you also have your total indirect effect above, which is your negative 0.278. Your orange is only specifying that one mediation effect you found most interested in. Regardless, in all cases here, those mediation effects are significant at the 0.05 level. Like the IND statement, the VIA statement would have your dependent variable or your criterion variable on the left-hand side, and on the far right-hand side would be your independent or predictor variables. All the variables in between would then be your mediator variables. In other words, the VIA statement requests all indirect effects between x to y that are mediated by m. Here, we're really testing whether the relationship between x1 and y2 is mediated through y1. The only difference here is that, just like before, you'd have all those individual tests for mediation. The addition here is you have the sum of, as you can see here in the results, just like before, you had those 3 mediation effects, but you also have the sum of those indirect effects. As it can be seen here, all 3 mediation effects are significant, as is the sum of the total indirect effects. Remember, it's a sum of all those indirect or mediation effects. Next, we're going to change our focus to moderation effects. Moderators, also called interaction or non-invariance, is a process of testing where the relationship between x and y differs based on the level of m. In other words, does m moderate the relationship between x and y. Again, a moderator in non-invariance is really the same thing. Moderation is really important as you want to know whether the strength relationship between two variables differs based on another variable. From a treatment standpoint, a treatment may be very effective for males, but not for females, thus suggesting that gender moderates that path. When testing for moderation effects, how you analyze your data really depends upon the type of data you have. When your variables or your moderators are categorical, it's often easiest to do a multi-group analysis. In other words, you have the entire model and you're testing whether it's invariant or equal across groups. This is basically the exact same thing we did last week, where we tested a given model and do those path coefficients, are those equal across groups? A very simple model could be you have an employee retention model and you want to know whether that model predicts equally well based on whether someone's a full or part-time employee. The only limitation would be if you had a lot of categories. If you had, let's say, 10 categories, testing whether that model is equal across 10 groups might be a little bit overwhelming. An alternative approach is to create interaction terms, where you only want to know whether certain paths are moderated. In this case, all you would have to do is take your predictor variable and multiply it by your moderator variable. The important caveat here is that your moderator variable can only have two categories, often dummy-coded -1 and 1 or 0 and 1. That product then would then be regressed upon the y variable, and if that path is significant, that would imply you have a significant moderation effect. Just like before, if you had 10 categories, you would then need 9 dummy codes, and that would be very overwhelming. So you may opt to choose to either collapse those categories or only look at certain levels of that moderator. When your moderators are continuous, you follow the exact same approach you would have in your other regression courses. Essentially, what's most commonly done is you center each of your variables, your x and your moderator variable, and then take the product of those two and use that as your interaction term or your moderation effect. In the equation here, you have y equals alpha 1. Of course, alpha 1 is your intercept, plus beta 1 x, which is your predictor variable, beta 2 m, which is your moderator variable, plus beta 3, which is the product of x and m. Now, if it's a significant moderation effect, beta 3 would be significant. Remember, beta 1 is a main effect, as is beta 2. Recall that if beta 3 is significant, that means you have a significant moderation effect, and the relationship between x on y differs at various levels of. Now that you understand these important terms, we will now test some path models using both mediators and moderators with an M+.